chapter 7 of these notes, we did quite a bit of work on frequency analysis, frequency domain analysis, and now is sort of is one of the payoffs, but there are a couple payoffs of it. In my experience, frequency response analysis is more powerful than time domain analysis in a lot of things. For a lot of applications, it's more powerful. However, I find root locus design of control systems to be a little nicer to work with than frequency response techniques for design. Nyquist, if you read the chapter on it, he goes so far as to call it an art, frequency response design. It's not something that you can't write a procedure down for, but it's more finicky. Root locus is more direct, and there aren't a lot of advantages to using frequency response techniques over root locus. The two advantages that arguments that can be made for advantages are that you can do frequency response design with pencil and paper a lot easier than you can do it for root locus design. You can actually do root locus design with pencil and paper too, because you can draw the root locus. You can find the gain for a given point by finding the lengths of the vectors from the poles and zeros to that test point. Nobody wants to do that. That's no fun. In the frequency response technique, there are a few different things that Nyquist talks about, a few different design techniques that he goes over. He goes over how to do proportional, which we'll do, and then he does lead, lag, and lag lead. And he shows procedures for those. But they're kind of specific to the problem at hand, and it's not always the same, the procedure that you walk through. So it's really just understanding the techniques we learned in Chapter 7, and then looking at a problem and coming up with a strategy for how to make the response do what you want. And it's only with the one that we're going to go over today, the gain one, that it's like a pretty straightforward technique that you can reproduce on lots of problems. But it's only gain control, and that's it. The lead and the lag lead stuff, there are some techniques, but they don't always work on everything. So I'm going to encourage you to lean more on root locus design for your controllers, but in some cases, it can be advantageous. And really, the only one place that frequency response shines over root locus is that when you design a lead controller can be designed to not only take care of the transient characteristics that you want, but you can simultaneously design it to compensate for your steady state error as well at the same time. So you remember in root locus design, we would arbitrarily set where the pole and zero were for the lead controller. The frequency response design gives you a way that's a little bit more straightforward to incorporate, to choose that based on also what your steady state response your desired steady state response or your steady state error is. So that's really like the only advantage, but then again, you could just add a lag on there separately. So you could do root locus and then it would be lag, but then it wouldn't be just a straight up lead, it would be a lag, a lead lag. So there is a slight advantage in that sense, but I don't know. I don't find that to be a big enough advantage, I guess, personally, to use it very much. But I think it's worth getting introduced to the, essentially learning to do the gain one unlocks kind of like the technique for you to go from the Bode plots and do the analysis. But when I do this example that I'll do, it'll kind of show you how they're all kind of done, but it's just one specific technique, and you can vary it. And you can kind of make up your own thing too. Like you can do, as long as what you're doing is reasonable, and you simulate and make sure things didn't get screwed up in the end, then you're good. So controller design is really like an open thing. You can kind of do whatever you want. It isn't like you have to do it a certain way. But I like root locus better. So I'm just going to do this and look ahead to chapter 9 is of these notes is actually on state space design. So next week I want to lecture on state space design and show you guys how to do that. And I'm debating about the final, because then we have one more week of lecture. I can't give you homework over it because it's the last week and you guys won't have time to get the homework turned around before finals. So I will lecture on something that I think is going to be fun. And I've got a couple topics that I might do. I might teach you guys how to do optimal control without like a lot of understanding of the theory, but just like high level and using MATLAB to gloss things. That's one possibility.
Could we learn a little bit how to do make a transfer function through experimental data? Not that's something I'd really like to learn.
That would be cool. Yeah, I would be fine. I mean, it's not something that is controls or robotics specific, but it's also very related to a lot of topics in controls and robotics. So, yeah, I would be fine with that if other people are interested. So the topics, maybe we could just do a vote or something on topics, because there's a little bit of optimal control we could do. We could do a discussion of digital control. That would be another possibility. We could do a discussion of like hardware for control. So those are some different ideas. So maybe we'll like do like a little poll and see what people want. Because it's going to be a topic that's not going to be on the final, because I'm going to give you guys a final exam in class on Wednesday. And so it's not like I'm going to be like, okay, here's some new information, and here's a final exam over this information. So I'm not going to do that to you. So yeah, that might be fun. Let's maybe like, can you do a poll on Slack? I feel like you can. It's probably possible. We should do a poll. Nice. Slash poll.
Just make a straw poll and link it in Slack as well.
Yeah. We could do a tribal council. Could do whatever. Or what do they do in Big Brother? What do they have? Not Big Brother. Isn't that what it's called? Big, no.
Top shot, they use handguns and shoot targets for not hurting them. So I think that's the best one we should really discuss here. Bring in some handguns.
Yeah. There you go.
Right after they had the incident over the weekend.
Yeah, exactly. I mean, we'll bring a 12 pack with us too. We'll just make this crazy.
Yeah.
Just
Great.
take over the engineering.
Let it be known that I was not condoning bringing guns to campus. Just want that to be stated for the record. I might have been smiling and giggling at that suggestion. Disapproving giggle.
Giving us the final in class.
I'm going to be giving it to you. It's a take-home.
Handing it.
Yeah.
Just handing
Wait, what is the take-home?
The final.
The final take-home?
Yeah. I'm making it a take-home because I like most of this. Yeah. Most of the stuff that we've gone over has been techniques that require MATLAB or something equivalent to MATLAB. And time, also. And it's design, so it's not like, it's really hard to sit down in front of a piece of paper and design a control system that's just a difficult task. And not having a computer and not having time to mess with it and simulate and get confused and all of that, that's just a regular part of the process. So yeah, so it'd be take home. And as I do this more and more for grad classes and for by the way, also the grad students in the class are going to have an extra problem on the final exam. So you're welcome. So the two main things in this class that you guys have done is the taking the lead on the project stuff, and then also doing a harder final exam. So I think you guys will have fun with it. So. Something to look forward to. Congratulations.
Isn't that one of those things you're supposed to say at the beginning of the semester?
Maybe. I don't know.
Right before my
they're in two different classes, so it says you have a final exam. So the fact that it's different is not something that I have to specify. So I can do whatever I want.
How much extra credit you putting on there?
On the grad student one?
On the final.
So you can still get.
Oh yeah, I don't know. Historically, it's been somewhere around 0. Yeah.
Okay.
Yeah.
What are the p-values?
So okay, so that's a little bit of an introduction to the frequency response design techniques, like an overview of them.
What if the undergrad students want extra credit for doing the graduate problem?
Ooh,
Sounds like a target.
that's not a bad idea. I kind of like that idea.
If you want.
And the grad students get extra credit for doing the undergrad project?
Sounds fair. So, okay. We're going to do transient response design by gain adjustment. So just pretty simple controller design, just a proportional controller. The following design procedure allows us to design for a desired percent overshoot. Okay? So that's what this procedure allows us to do. Like I said, a lot of these are very specific to a specific task and a specific problem. Percent overshoot and damping ratio, they're very tightly coupled. Those two are the easiest parameters to design for, time response parameters to design for, because they are directly related to some frequency domain objects. So this is the procedure. Generate open loop Boda plots with some convenient initial gain Ki. We'll talk about this convenient initial gain. Use either figure 7.8 or equation 7.24 and equation 7.25 to find the desired phase margin phi m. So you're given a desired damping ratio or a desired percent overshoot, and these equations in that figure relate percent overshoot to phase margin. Okay? Directly. They're directly related. And it's not like, so the gain margin depends on a few parameters that are coupled, but phase margin is just directly related to percent overshoot and damping ratio, which are essentially equivalent. So step 3, from the Boda phase plot, determine the frequency at which the phase is equal to the desired phase margin. And step 4 is to change the gain to be such that the magnitude plot would intersect 0 dB at that frequency, making the phase margin the phase that you want. So moving the magnitude plot around so that you get the phase margin that you desire. So when we adjust the gain, if you think about it in terms of the Boda plot, what are we adjusting? Do we change the phase diagram at all? No, the phase is not at all. It's just the magnitude. Yeah, so just moving the magnitude up and down. And that changes the location of the phase margin definition. So we can essentially dial in a phase margin by adjusting the gain. And that's this technique essentially comes down to that. It's pretty straightforward. And actually, it's pretty easy when you look at it in a Bode plot. It's pretty straightforward in a Bode plot. But there are some things to watch out for and some caveats, and when we walk through this problem, we'll see some of them. So here's the example that we'll do. Example 8.1, percent overshoot design by adjusting the gain. So design a unity feedback gain controller for a system with this plant, such that the percent overshoot is approximately 20%. So that's our goal. We have a transfer function. Let's think about this transfer function for just a moment. Like, what are we working with here? So comment on this transfer function for me.
There's no zeros.
No zeros. Okay, so that's one thing. Yeah, what else do we know about it?
Slow system.
Sorry?
It's a slow response system because all the poles are far to the left.
Yeah, the plant poles are far to the left, so it's gonna respond slowly.
Transients faster.
Oh yeah, you're right. Sorry, Sirac convinced me. You were very convincing. Yeah, so they're gonna die out really quickly, right? Because they're large negative exponents, so they'll die out quickly. So they're gonna be. It's a very quick response. And
So we got a gain of 10, right?
yeah, the gain. Well, so there are a couple different things here. If you want to talk about the DC gain of a system, that's the gain at zero frequency. So if you just had a constant input, and you find that by just setting S to 0. So the gain for this system when S is 0 is actually 10 divided by 90 times 30. So that's really small DC gain. But it does have this like gain term in the numerator that we do need to make sure we watch out for of 10. So sometimes when we refer to the gain of a transfer function, we're referring to that DC gain value. Sometimes we're referring to whatever that numerator is. So it just depends on the context. We just got to be aware of the two possibilities. And then also it's stable, right? So the open loop transfer function is stable, which is good news. So if our thinking in terms of Nyquist here, our number of open loop poles in the right half plane is 0, right? That means that we need 0 encirclements of -1 for stability. If we had like one pole in the right half plane in open loop, we would need at least one counterclockwise encirclement of -1, but we don't need that. So we're expecting. So we know that this thing is stable to start. The open loop is stable. But it could have a clockwise encirclement of -1 on the Nyquist plot, which could make it go unstable at a certain gain. So we would expect that low gain the system is going to be stable, but it's possible that at high gain it's not going to be stable. So let's take a look at the Nyquist plot first. And so I just define ZPK. I define the two poles, no zeros, 2 poles, and our gain of 10. So let's examine the Nyquist plot first. Crap. Gets me every time. So, what are we... I don't like us to tie one hand behind our back during problems. We're trying not to lean on root locus here. But this is such an easy root locus that it's hard not to think about, right? What's the root locus look like for this?
2 points. 2 points. 2 points go and then go off in infinity. Right?
Yeah. So actually, do we think that it's going to go unstable if we increase the gain? We don't really expect it to go unstable, which is something we should be able to verify with this Nyquist diagram, right? So let's see if we can interpret that both ways. Let's interpret it. Oh, yeah. I guess since I restarted MATLAB, I should also execute the cell above again. Seems reasonable. It was a reasonable request. MATLAB wasn't being unreasonable that time. Usually it is. But. So here's our Nyquist diagram. This is -1 on the real axis. And here is the contour, which is all happening down here. We can't even really see it, right? It's all very small. 10 to the -3 on the y-axis and some fraction of 1 on the real axis. So we zoom in, and what we see is this cardioid with one cusp in it that is coming into 0 here and has how many intersections with the negative real axis? Well, it's hard to tell for sure, but it looks kind of like there are none. I mean, it looks kind of like it just goes to 0 and never actually crosses over the axis, right? I mean, it's possible that there could be a little loop here that we can't see because of the resolution, but just from looking at this, it does not look like there is any crossing. And if there is one, it's super, super tiny, which means that if there is one, there's probably a lot of room for the gain to increase. And if we could scale this thing out, right, by multiplying it by a gain. So if we were concerned, we could multiply this thing by a gain of like 1 billion, and then we could plot this again, right? And we should see this whole thing expand out, but if it really doesn't have any negative millions, yes. If it really doesn't have a crossing of the negative real axis, then it's always going to come back to 0 at that cusp. So that would be one way to test it. But it looks, I mean, this looks exactly like what we're expecting from our root locus analysis, right? Our root locus analysis that we didn't do, but we just did in our minds, right? That we're just like, oh yeah, no locus, locus in between these two poles on the real axis, no locus. There are no zeros, so they're going to have 2 zeros at infinity. So that's going to divide the plane into 2, and they're going to be up and down, and so it's just going to come together, and it's going to go straight up and down. So we've seen that before, so we're comfortable with that system. And we know, oh yeah, any gain is going to be fine because the root locus never goes into the right half plane. But this Nyquist diagram is good to take a look at that. So let's think in terms of, so we're going to be using the phase margin, but since we're still getting used to Nyquist diagrams, let's talk about phase margin and gain margin here. Do you guys remember the definitions in terms of the Nyquist plot?
The magnitude at which it crosses that arc and then the angle that is.
Yeah, so the gain margin depends on the distance between the real axis crossing, hopefully single real axis crossing, and -1. So the negative real axis crossing and -1, not this positive real axis, negative real axis crossing and -1. But it appears that we are never, and it doesn't matter how much gain you increase, you're never going to make this thing have a real axis crossing, negative real axis crossing. And therefore, your gain margin is infinite. Yeah, you have an infinite gain margin. Okay. Your phase margin, you might recall, is defined as what the phase is of the Nyquist plot when it crosses the unit circle as it heads towards the origin. And so we are real zoomed in right now. Is this thing ever going to leave the unit circle?
Most likely not.
No, it's not. Because I mean, if you see it, and this is the whole contour here. You goes around, and then it comes back, and this is at 10 to the minus 3. 5 times 10 to the minus 3, and this is at negative 1 times 10 to the minus 3. This thing never leaves the unit circle. It's all contained inside. So the phase margin is just undefined because there's no crossing. It never leaves, so it can never come back.
If we have a giant gain, couldn't it possibly cross?
That's right. Exactly. So that's what this initial convenient gain is going to be about for us. We don't have this. So if we scale this thing up, then it will eventually leave the unit circle, and then it will come back. So that means that we will have a phase margin that's defined. So if we increase the gain, we'll start to have a phase margin. So that's what we're going to do to sort of start this thing, is to start with a convenient gain. It's actually unnecessary to really do it, but it makes people feel better to start with an initial gain, so that actually a phase margin is defined then. And then we start to change the phase margin. But technically, you didn't have to make it defined before you started changing it. So, but we'll do it. Determining how much you need to increase the gain margin, or increase the gain to get the phase margin to be defined, is kind of difficult. From this plot, I mean, you have to figure out at what point, when you start leaving and all that. But it's going to make a lot more sense from the Bode plot. So let's check out the Bode plot. So we see that this magnitude starts out, negative 50 almost dB down here, and then it rolls off down. So it never goes through magnitude 1 like we expect. It's always small. So it should go through 0 dB, right? If it's at magnitude 1. So we never get there. So we have to increase this by a gain, and how much we increase it, we just need to increase it so that this is above 0 dB, right? So that's all we need to do. So we can just pick this off and say negative 48.6 dB. So if we increase the gain by, if we just did 50 dB, we would shift this whole thing up so there would be a 0 dB crossing, right? Which means that, in terms of the Nyquist plot, that the unit circle is left and that we return to. So that's our first thing, is to find an initial gain. So if we scale it by 50 dB, we're good, but then you have to compute what that is, not in dB, because when you multiply it by the transfer function, it can't be in dB. So you have to find that in magnitude terms. And there's this nice little function, dB2mag, you can use, or you can just use the formula. So dB2mag of 50 gives us the magnitude. And then we take our open loop system and we scale it by this convenient gain. And let's look at the Bode plot for that. So now it starts above 0 slightly, and then it falls below 0 at some point. So if we take a cursor and we go along, dB of 1, and then cross 0 right about there. So now we have a phase margin. The phase margin is going to be what?
It's the phase at which you cross that 0 dB, right? Straight
Yeah, well, it's the phase above negative 180 degrees. Yeah, so if you take this, you go down to here, and I guess this is the same point. Then our phase is at negative 41.7. the phase margin is defined as the amount above negative 180 that we are at that point. So you take 180 minus 42, and that, I think yeah, so that would be our phase margin. I didn't write it down because we actually don't care about it. It's going to be 138, right? 138 degrees phase margin, which in terms of our performance, our time response performance, that's way too big. Okay, so let's find out. What do I mean by way too big? Let's look at. See if I've got it open here. Let's look at. Nope. This figure. Must have passed. Well, it's going to be in this one anyway. So in the frequency response analysis chapter, if we go down to Nyquist stuff. There we go. I saw them. Aha! Phase margin related to percent overshoot. Also, you could use these formulas, but we don't need to do that. Those equations suck. So, I mean, we could use them, we could program them in, and we could never have to program them in again, but for purposes of this example, we're just going to use the chart because we're not crazy. Notice that down here there's a phase margin to damping ratio relationship. So phase margin that high actually isn't even defined on percent overshoot, and then the reason is that you have no overshoot. It's going to be over damped. If you look at where the damping ratio is for phase margins as you go up, the damping ratio is increasing, and it's above 1 at like 75 degrees. So those large phase margins are much too big. So we don't want that phase margin. Not surprisingly, we just sort of stabbed in the dark and found a gain that got us above 0. So let's find one that we actually want. And so let's look at this graph to find out what we want. So we want, not the damping one, the percent overshoot one. We want a 20% overshoot, right? So 20%, so it's like 47, 48 as a phase margin, somewhere in there. So that's what we want our phase margin to be in degrees. That should have been labeled. Okay, so we want it to be 47, 48 degrees, which, so this is why I say, this is what we want, 48 degrees, let's say a phase margin. So this phase occurs at a frequency of about 130 radians per second. We know that from this. So a phase margin of 48 occurs at a phase of negative 132, right? Is that right? And within the accuracy of these points, I could get a little closer if I put more points in my Bode plot.
What did you just do?
So I want a phase margin of 48 degrees. So I need to be 48 degrees above negative 180.
Oh.
And so I need to find out at which frequency that occurs. And so this is where I want my phase margin to be, approximately. So if I took 180 minus 48, I'm going to get 132, right? And so 133 is pretty close. It's about as close. I mean, I can get a little bit tighter if I put more points in here, but this is not a bad start. So at about 130 radians per second, that's the point at which we want the phase margin to be defined, which means this is where we want the gain, the magnitude, to go through 0 dB, right? We want this magnitude plot to go through 0 dB there, so that at this phase, or at this frequency, this is our phase margin, right? And the way that we do that is we essentially shift this whole magnitude plot up until this point reaches 0 dB, and that will then make this our phase margin. So let's try it. So if I come here and I say, okay, so at 131, so the same frequency, I have a magnitude of negative 16.6 dB. If I added 16.6 dB to this, meaning I multiplied by a gain of whatever the magnitude version of 16.6 dB is, this is going to go through 0 dB. It's just going to shift this up to 0 dB. And so let's do that. So our gain for the system is going to be our initial gain, the gain that we used to just get a definition of the phase margin in the first place, multiplied by 16.6 dB in terms of magnitude. Which, if we were to, and I didn't include this, but we could easily do so. So let's do a figure bota of k times cis open loop.
You type
Body. But my body. No? No? Okay. I'll do grid on. Grid on is good. So we are now crossing 0 dB out here. So let's find out at what frequency approximately. Well, that's pretty close. So 131. So we pretty much dialed it right in, right? And at that same frequency, we are at, let's see. Yeah, that frequency. We are at negative 133, which gives us a phase margin of 47 degrees. So that's pretty close. I mean, it maybe could be a little bit better, but it's not bad. I mean, we could have gotten better if we had tried a little harder, but we didn't. So our phase margin then is what we want according to these transient response characteristics that we derived for second order systems back in chapter 7. And we're predicting that we're going to be close to 20% overshoot here. If we use that gain, we're going to be about 20% overshoot, which is our design goal. So let's give it a shot. Feedback. Use the gain that we derived there. Let's print out what the gain is. So it's pretty big. So 2100 is our gain. No units on that because we weren't given any units, so don't really know how reasonable that number is for a gain. But that's fine. We don't care because we're not going to go unstable. We know that. We already determined that, which is a good thing to do at the very beginning, is say, what range of gain is going to be stable? Because if your bota plot design can lead you very wrong unless you're always checking back the Nyquist plot. Make sure that you're not going to go unstable, because the bota plot will not give you a warning of that occurrence necessarily. It's more subtle. So let's take a look at the step response of this. Well, it looks like our overshoot, 26, 27%. It's a little high, a little higher than we wanted, which is, but it's in the ballpark. So that when your first design is in the ballpark, you think success. So we were pretty close. So now all we need to do, you could do a few things. You could either just tweak this gain, probably the easiest thing to do, just tweak the gain and keep checking the overshoot, because that's probably going to be a pretty fast way to converge to the percent overshoot that you want. Or we could go back and do a second iteration. So let's do a larger phase margin. Let's just shoot for a little larger phase margin. So instead of 48 degrees, we'll go a little larger. We'll go to 55 degrees. That corresponds to on this, well, you have to always go back to your original Bode plot. Or actually not your original, the one that you already did KI for, but I blasted that away. What did I do? This one.
What did it say your overshoot was?
26.
That does something wrong there, never mind. I knew it was 0 overshoot, so I don't know why I did something wrong.
Well, we'll take a look.
I was trying to follow along what you were doing, so I should have been at that step.
Yeah, let's let's debug. Let's debug what you're doing too, because it would be kind of a good experience, I think, for everyone to see it. So okay, so if we wanted a 55 degrees, we were gonna move to the left here, right? Because so 45 or 55 degrees is gonna mean we want a 35. 125, yeah, math. 125 degrees here, so approximately there, right? So frequency of about 112. So that's what I came up with there. And then at that frequency, we have to figure out how much magnitude to increase, which is 14.4 dB to get to 0. So that's why we choose 14.4. Then we just do the same thing again. And 22% overshoot. So we're getting close. Quite frankly, we're just changing the gain manually is probably the way to go from here. But we could do a third iteration to 60 degrees of phase margin. And goodness, I bet this is going to work. What do you guys think? Oh, look, 18.4. So we actually undershot or whatever. And somewhere in there, we could iterate some more if we wanted to. Or we could just adjust the gain iteratively. When you get to this point, I actually, going back and choosing a different phase margin it's just more work, because you know this is a monotonic function and the gain is going to decrease if you go one way and increase if you go the other way. So instead of picking out a phase margin to iterate on, you might as well pick out a gain to iterate on, because they're essentially equivalent in this case. So yeah, I would just probably adjust the gain around until you got the overshoot that you wanted. Yeah. Of course, so this kind of concludes that example. I did want to mention as well that steady state response compensation is essentially the same as it is for root locus steady state compensation, because you're either going to add in you could add in a pole, so you can do PID stuff. You could just add in an integrator, and you would improve the steady state situation. You can just do that ad hoc if you want to, or you could design it based on, you could do a lag. And there are some lag design, there's a lag design example in Nice if you wanted to look at how they do that. Essentially, it all comes down to shaping the Bode plot. So the types of types of systems that, I guess the analysis that you do is essentially shaping what this Bode plot looks like, because the response characteristics that we determined in this chapter relate for us the phase margin and the gain margin that you can read off the Bode plot pretty easily, like we were doing, to these time domain characteristics. But if you look at like the bandwidth, which is pretty easy to compute, it's related to zeta and the settling time and the peak time. And so that one's a little bit more involved and complex. And so it's harder to tease it out with those. It's a little easier to use the percent overshoot as your goal.
So if you're going to try to use the Bode plot to do steady state and stuff, would you try to put an inflection point, another inflection point in there or something? Try to change that?
Yeah, so if you think about how a pole affects a Bode plot, do you guys remember how
Change the
Change the
slope,
slope,
right?
make it
changes the slope? Yeah, and it changes the slope. It changes essentially like the slope at low frequency, the low frequency slope, which affects this whole graph, right? So if you have a 0 at the origin, then it's an up slope. If you have a pole, it's a down slope. So yeah, that's how it affects it. So you can shape this diagram with that, and you can try to get the phase margin to be a certain thing, or the gain margin to be a certain thing. And that's really what all these techniques come down to, is shaping this and thinking about. And this is when you're doing your Bode plot sketching helps you. That's one of the ways that it helps you, because you can start to think about how putting a pole here, a 0 here, is going to affect the shape of your Bode plot. Instead of just ad hoc trying to shape it. Yeah.
So when you're shaping it too, because the Bode plot doesn't tell you you go unstable.
Yeah.
So then how
You
do you
gotta be
shape
cautious.
that?
So you can always go back to the Nyquist plot. And so that's actually, it's not part of the procedure that Nice recommends. It's, if you start out with a stable system, chances are that if you increase the gain enough, it's going to go unstable. And you'll be able to know that when your gain margin and phase margin start to become negative. And so you can tell that on the Bode plot. You can see if the gain margin or phase margin have gone negative. So, for instance, if our we never reached negative 180 degrees with this phase, right? Which means that we never crossed that negative real axis. If, however, but we do have a phase margin, so you can see when the phase margin goes negative, that's a sign of instability, or potential instability that's going on. So what we need to do is we need to make sure that at 0 dB, the 0 dB crossing, there is some positive phase margin. We're not below negative 180 degrees at 0 dB. Notice that we can never be below negative 180 degrees for this system, because you can go up to very, very high frequencies, infinitely high frequencies, and never quite reach negative 180 degrees. So that can never happen for this system. But other systems have crossings of negative 180, and if you increase the gain to a certain point, that's gonna be an issue. So, for instance, you're never supposed to do this, but I think I can come up with an example off the top of my head. Let's see if we can do it. This is what people who teach, and like you start teaching, they say never do an example that you haven't prepared previously. So I'm gonna do just that.
Oh,
Yeah, so let's do it with another pole on the real axis. Okay.
It's like an acetylene.
Yeah. Yeah. So I believe that this system there's going to be a gain because I think that they're going to go off like a sideways peace sign, and then at a high enough gain, it's going to cross the j omega axis. That's how I feel. We could do just for fun. We could do an R locus of cis OL. Did I not define that? Okay, so that makes sense. We know there's going to be some gain where it's going to cross over, right? But say we're just like we're pre-root locus because that's what the situation was. The frequency response stuff came first, actually. You're pre-root locus, and you're going to look at the Nyquist plot for this. Okay, so it looks kind of similar, but we zoom in, and there's a loop. And that loop means that at some point, when we keep increasing this gain, we're going to have encirclements. Now, we also should check in what direction they're going to be. They're going to be a clockwise encirclement. Actually, they're going to be two clockwise encirclements. And that's bad news. We do not, we have no poles in the right half plane to start, so we're good to start, but if we increase the gain, we're going to have two encirclements. So that's the thing we got to worry about. If we, went forward on this problem, we could look at the Bode plot. We could see that the phase does go below negative 180 degrees. So at a certain point, if you increase the gain, you're going to move this magnitude plot up to a point where you start to have 0 dB crossings. And at a certain point, those 0 dB crossings are going to start to occur further and further out this way, right? So if you keep moving this magnitude plot up with the gain, then those axis crossings will occur further to the right. And that means that your phase margins will be measured further to the right. And so when you're out here, when you're at frequencies higher than, whatever this is, looks like it's like 80 radians per second or something. 80 radians per second and higher, if your 0 dB crossing is 80 dB or higher, you're going to be unstable. So let's see if our little reading of graphs is very good. So somewhere around, we'll say there. So we'll say 68 radians per second is somewhere around that crossover point. That means that we can increase the dB. We can do like a 95 dB increase, but if we go more than that, we're going to be unstable. What is that in magnitude? What did I say, 95? So 56,000. And if we come back, did I close the root locus plot? I think I did. What do you guys think this is going to look like? 56,000? 70,000. That's 56,000. So, yeah, we need a little bit better resolution. But this is 56,000. Well, it's 57, 58,000. So somewhere in there. So this is the point. This is the gain crossover point. So we know how to do this with root locus, finding the gain that becomes unstable. But now we can kind of see how to do that with a Bode plot as well, looking in terms of phase margins and gain margins. Yeah. You could also do it with a Nyquist diagram, right? Because we could bump the gain up on this. So we're just playing at this point, but I think that it's good to do. So like we could do 56 E3, and we're getting close. Yeah, so we could bump it up. Let's do like 65,000. So we could interpret this from the Nyquist plot. We could do, I mean, we have lots of ways to cut it now, but the more ways you can analyze the system, the better, the more intuition you're going to have for it and how it's going to behave. So, yeah. And then we could continue this, the design that we are working on now, we could do the design 20% overshoot design with this system as well, right? We would just have to make sure that we don't increase the gain too much. It'll be obvious if we do in our simulation. It'll be very obvious. But we don't expect to. It would be an accident if it happened, because we're shooting for a positive gain margin, or a positive phase margin, right? And if we ended up with a negative phase margin, then we would have had made a mistake at some point. So we don't want, I mean, one of the easiest ways to make a mistake here is to forget that you have to measure from negative 180 up for the phase margin. If you went down for the phase margin, you would already be unstable, and you would have to recognize that. So with the Bode plot, you look at it, it doesn't leap out at you that there's a certain gain at which this system goes unstable. It does when you look at the root locus plot, right? It's like, oh, clearly this goes unstable. The information is in there. It's sort of just more hidden. Same with the Nyquist. It's more obvious in the Nyquist than it is in the Bode that it goes unstable, because the encirclements thing is pretty easy to see. But the Bode is easier to work with for designing how much to increase the gain and all that. So that's why we work with the Bode plot. So, okay, any other questions on this problem?
Are you posting that code somewhere?
Yes, I already sent it out. Yeah.
That's why I didn't see it. I was expecting your website.
Yeah, I've been sending stuff on Slack for this, just because there's been a lot of code and all that.
Looking in the wrong spots, all that.
Yeah. Okay. So if there's nothing else, that's all that I wanted to cover today for theory.